Alright, this video is on scatterplots and correlation. So hopefully by the end of the video you totally understand what a scatterplot is and you definitely understand what correlation means. So first off, let's begin by understanding that many statistical studies examine the relationship between two variables at the same time. A couple examples I have, for example, number one, the number of goals a soccer team scores in a year and how many wins they have in that year. I'm assuming that there is a very simple relationship between the number of total goals a soccer team scores in a year and the number of wins that that team has for that year. Another example here could be the number of miles on a used car and the price of that used car. Again, I'm sure that there is definitely a relationship between the number of miles on a car and how much you could sell that car for. And third is the gender of a person and depression. I am very certain that there is probably some type of association, some type of relationship between the gender of a person and whether or not they have depression. Now, those are just a few examples. Now, the first thing we're going to talk about is actually naming the two variables that you have. Obviously, we're going to focus on two variables at a time. Now, we have two different types of variables. We first have the explanatory variable and the response variable. The explanatory variable is the variable that does the explaining. Does the explaining. I don't want to say it's the variable that does the causing because it's not that X causes Y or that variable 1 causes variable 2, but it's the one that does the explaining. And you have to sometimes just use your brain and kind of common sense to figure out which variable is actually doing the explaining. We call this the independent variable, meaning it's independent of anything else. It is what it is, and that particular variable explains the response variable. It's easy to understand that the explanatory variable is also known as the X variable when it comes to graphing. So remember, the explanatory variable is the X variable. The response variable is the variable that changes due to the explanatory variable. So the response variable is known as the dependent variable because it depends on the independent variable. So once again, the dependent variable depends upon the explanatory variable to have it change. The response variable is the Y variable when it comes to graphing, and again, the explanatory variable is easy to remember because it's the X variable. So let's go back to my examples here so we can identify which one is the explanatory variable and which one's the response variable. So in the case number one, the number of goals, the more goals a soccer team scores in a year, I'm assuming that will lead to more wins. If you score less goals, then it may lead to less wins. Now, it's not a guarantee. It's not always going to be that way, but the explanatory variable would probably be the number of goals that they score, and scoring more goals would respond into more wins. So this would be the response variable. Once again, the number of miles on a car, that explains why a car may cost less or more money. So the explanatory variable is the number of miles, and the response variable is the price of the car. Lastly, I got done talking about how the gender of a person could affect their depression, and that means that it's the gender that's doing the affecting. So the gender is the explanatory variable, where depression would be the response variable. Now, some of these examples here might have strong relationships and some might have very weak relationships, but that is certainly part of the study or the examination of those two variables. So what do we do once we have these two variables? Well, one of the most important things we do is we make a scatterplot of them. So let's talk about a scatterplot real quick and define them. A scatterplot is defined as shows the relationship. So again, it's like a picture of the relationship between two quantitative variables on the same, measured on the same individual. So again, a scatter plot is a graph, or it's a picture that shows the relationship between two quantitative variables measured on the same individual. Now, I'm going to go back to our examples and talk about what the scatter plots could look like. And again, if you need to pause to take the notes, feel free. Now, what do I talk about measuring the same individual? Well, I'm talking about in 1 year. Let's say in 1 year, a team scores 102 goals and they get 11 wins. So I would take this and turn it into a point where X is the number of goals they score and Y, the response variable, is the number of wins. And maybe another year they score 152 wins, or sorry, they get 152 goals and they win 21 games. Maybe another year they only score 50 goals and they only win 3 games. Again, I could take all these points measured from each individual year and create a scatter plot. Maybe I have a bunch of cars and one car has 9,000 miles on it, and that one car cost $20,000. Okay, and that would be measured in $20,000. So maybe another car has 51,000 miles on it, and it is selling only for $3,000. Okay, so you can get how I could create these points. Now, this next variable, these are not quantitative variables. Gender is categorical, male or female. How depressed are you could be categorical, could be quantitative if you make a scalar somehow, but since one variable is not quantitative, you can't make a scatter plot with categorical data. So we're only going to focus on the two variables being quantitative. So that doesn't mean that we don't examine the relationship between categorical variables, but for the sake of using scatter plots, they have to be quantitative variables. Okay, so let's take a look at several examples just so you can start to see some pictures of scatter plots. This first one up here shows husband's age and wife's age. So it looked at several married couples, and it looked at the husband's age and it looked at the wife's age. So every point represents a married couple, with the x coordinate being the husband's age and the y coordinate being the wife's age. Here's another one that shows the heights of people and the weights of people. So we looked at the heights in pounds of several, this is children, and then we looked at their heights in inches. Obviously 20 pounds would be, just a toddler maybe or something. So anyway, once again, all these dots, each dot represents one individual, and they were measured twice. We measured their weight, and we measured their height, and we created that scatter plot. Here's another one of average daily temperature and the number of visitors at a beach. Once again, both quantitative data, and we see that each day represented a year, or each point represents a year, and we looked at what was the average daily temperature during that year and how many visitors went to the beach. Here's another one that deals with working. When you have more years of experience, usually you have a higher income. So the X variable is how many years of experience you have, and then we talk about what is your income in thousands of dollars. So $30,000, $35,000, $40,000, $50,000. Here's another one here that shows the weight of a car in tons and the miles per gallon that car gets. And we see that each point represents a car, and the x coordinate would be the car's weight. That's the explanatory variable. And the response variable is what's that car's gas mileage in miles per gallon. Here's another one here. I don't have any specific variables attached to it. I'm just going to make one up. For example, the x-axis here could be amount of water, or amount of rain, I guess you could say. And the y-axis could be the yield of crop, how much of a particular crop we get. So yield of a crop. So for example, corn, right? And the idea is that if we just give it a little bit of water, we're not going to get a whole lot of growth, and we're going to have bad crop. If we give this nice, perfect amount of rain, a good, nice amount of rain, not too little rain, not too much rain, we're going to get a lot of crop. But if we get too much rain, we get flooding, and flooding also kills the crop, so we don't get as much crop. So we see that type of scatter plot as well. Now, when we look at a scatter plot, we want to be able to examine a scatter plot. So examining a scatter plot is a huge part of this particular unit. Now, there are 4 things that you need to do if you are asked to examine or describe a scatter plot. Make sure you take note of these 4 things, make sure you write them down, and make sure you memorize them. The first thing you must tell about a scatter plot is its direction. The direction of a scatter plot is either going to have a positive direction or it's going to have a, whoop, I don't know what I was right there, it's going to have a negative direction. And that comes just from looking at the scatter plot. As x goes up, does y go up? Or does x go up, does y go down? Remember, the x variable is always going up. If y also goes up, it's positive. If y goes down, it's negative. Okay, what is the form of the scatter plot? Is it linear, meaning do the dots appear to make a line? Is it curved, meaning do the dots appear to be making a curve in the scatter plot? Or do you see something like a parabola? Maybe you see a curve that goes up and then comes back down. Again, what do you see as the form of the scatter plot? And to make that kind of a general, just kind of squint your eyes and say, what do I see? Do I see a line or do I see a curve? The strength of a scatter plot, how strong is it? So the more tightly compact the points are, the stronger it is. The easier it is for you to see form and for you to see direction, the stronger the scatter plot is. So we have strong scatter plots. If it's very hard for you to see the direction or to see a particular form, then you probably have a very weak scatter plot. Now feel free to use some adjectives like very weak or very strong or moderately strong, moderatively weak. Don't forget you could throw some adjectives in there to make describing the strength easier. The last thing you need if you're going to examine a scatter plot is some type of general statement. Notice something like saying, hey, I noticed that as the average daily temperature goes up, there does seem to be a tendency that the number of people that go to the beach also goes up. So the general statement must be what we call in context. In context means don't just say X, don't just say Y. Use the variables that are defined in the problem. Lastly, obviously, if you do see any outliers that don't seem to fit the pattern, point them out. So I guess that would be kind of like a number 5. So let's go all the way back to our examples here, and let's talk about what we see. Okay, if I were to ask you to describe the scatter plot between husbands and wives' age, you would definitely say positive. That's pretty easy to see. You would definitely say linear. I see a line. Now, anybody could look at that long enough and see that they see a slight curve or a teeny tiny curve, but overall, I would say the pattern is very linear. And we also notice that it is very strong. Those points are all very close together. It's very simple and easy for me to see positive and linear, so I would say very strong. And then lastly, a general statement would say something like, the graph shows that there is a tendency as husbands' ages go up, so do their wives. Or there's a tendency that husbands and wives have similar ages. For example, if a husband is 55, the wife is around 50. That's pretty close. Or you could even say something like it appears that wives are usually around 5 years younger than their husbands. Again, just some type of general pattern. Avoid the word cause, though, because we all know that a husband's wife does not directly cause the wife's age to be younger or older. All right, in over here, we're talking about the weights and we're talking about the heights. Again, we see positive, we see linear, maybe moderately strong. There is a little bit of scatter there, but it was very easy to see a strong straight line. We also have a general statement that as a child's weight goes up, it appears that there's a tendency for their height to go up as well, and that's pretty common with any human being. If you weigh more, you have a tendency to maybe be taller. Now, that's not true for everybody, but that's okay. No one said that this has to be true for everybody. It's just a general statement. Once again, beach visitors, we also see a positive, fairly linear relationship. And again, it's, I don't know, in terms of strength, I mean, it's pretty strong. It's not weak by any means, but, we see one point here that doesn't seem to exactly fit the pattern. But overall, we see this upward motion where if the daily temperature is higher at the beach is going to have a tendency to get more visitors. So notice how I'm describing this in actually you could do it in 2 sentences. The first sentence can mention shape, form, direction, and strength all at once. For example, this scatter plot appears to be positive, fairly strong, and linear. One sentence I covered all 3 things. And then that final sentence saying, you know what, it does appear that as the temperature goes up, the amount of visitors also has a tendency to go up. Over here, we would probably say positive as well for the years of experience versus income, but I definitely see a curve there. I hope everybody could definitely see a curve starting. So I would definitely call that a curved relationship that is actually pretty strong. Those dots do seem to clearly make a curve. As the number of years, now to describe this, you got to be a little bit careful because it's curved, right? So you'd say something like, at first, when you get more years of experience, your income goes up pretty quickly, but as you get more and more experience, your income starts to increase, but at a slower rate. And that is something that you could easily see in a curved relationship. Here's one that is definitely negative. I guess linear. Again, it does look pretty straight. You might see a slight curve at the end there, but overall fairly straight. And the fact that I'm kind of struggling to say linear or curved means that it's probably not weak, but I would say moderately strong or kind of strong. Again, I wouldn't use the word very, but I definitely see positive, or sorry, negative. If you could see the direction very clearly, I don't think I would say weak at all. And this shows me that in general, if a car weighs more, that car is going to have a lower miles per gallon. Okay, here's one where I would definitely say, well, it's not really positive or negative, it's both because it has that parabolic curve. And then I would say something like, as the amount of rain goes up, my crop yield goes up, but when I get to a certain point, I get too much rain, and my crop yield starts to go down. So again, being able to describe direction, form, strength, and give that general statement when you're analyzing a scatterplot. All right, now I want to quickly show you on your calculator how to make a scatterplot. So the first thing I want to do is give you an example. So does the number of boats registered in the state of Florida impact the number of manatee deaths? Manatees are like sea cows. They're large animals that like to hang around boats. But the problem is if you like to hang around boats, you sometimes get hit by the propeller, and that could cause death. So we looked at several years of past data, and for each year we recorded how many boats there were in the thousands and how many manatee deaths there were. So the first thing I do is I enter the data into my calculator. List 1 here is the number of boats per year, or in a given year, how many boats are registered in the thousands. So this is 447,000 boats. Florida's a state that has a lot of boats because it's surrounded by water. And then how many manatees were recorded as dying that year. Now obviously more manatees could die for other reasons, but this is just what was recorded. So again, 13. The next one had 460,000 boats registered and 21 deaths that year. And again, this list goes on for, I believe, 35 years worth of data. Once you have your data in, hit y equals and make sure that nothing is there. Then you're going to go to second y equals to your stat plot. Go to plot 1, turn it on. Highlight the little graph that looks exactly like a scatter plot and make sure it's highlighted. And then make sure that your X list is list 1, your Y list is list 2. Now, if you flip those lists or you put them in list 3 and list 5, for whatever reason, you would make adjustments there. But I did put the X, which is the number of boats, is the explanatory variable, list 1, and the number of manatee deaths, list 2, as a response variable, Y. Once that's all done, you can just go back to your home screen. Make sure you do zoom 9 to zoom in on the data, and you get a beautiful picture of the scatter plot. Let's talk about the scatter plot. Well, I definitely see linear, positive, very strong pattern. It appears that if there's more boats registered in the state of Florida, unfortunately, there's more manatee deaths. That doesn't mean that boats are necessarily causing all of the deaths. It's just showing that there is a relationship there. Okay, now, how can we actually measure the strength, direction, and form of a relationship without vaguely using words? I mean, when I went through all those examples, I did a nice job, but I was just kind of speaking in very vague terms about kind of strong, a little bit strong, or I'm not sure if that's strong or weak, or I guess it's curved, but maybe it could be linear. So we want to find a way to actually measure strength, direction, and form of a linear relationship. And we, believe it or not, we can do this with a value called R. R is known as the correlation coefficient. The correlation coefficient. This word correlation is a very, 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 very specific word. Correlation measures the strength, direction of a linear relationship. So we got to be very, very careful to understand that correlation doesn't just measure anything. It's got to be the strength and the direction and of a linear relationship between two quantitative variables. So correlation measures the strength, it measures the direction of two quantitative variables. So if it's not quantitative, or if one of them is not quantitative, don't use the word correlation. Quantitative variables that form a linear pattern. So correlation only works if the data does appear to be linear, form a linear pattern. We're going to talk about a lot about this over the course of the next couple of moments, but understand that correlation measures strength and direction between two quantitative variables that form a linear pattern. So if you don't form a linear pattern, please don't use the word correlation. All right, now the correlation coefficient R, again, shows strength and direction of correlation. It is a number that ranges, okay? So correlation is a number that ranges anywhere from -1 to +1. +1 is very strong and -1 is very strong, but the negative just means it's a negative relationship going down, and the positive means it's a positive relationship going up. The closer you are to 0, the weaker you are. In fact, a correlation of 0 shows that there is no strength, there is no relationship between the two quantitative variables. Basically, here you can see a giant swarm of points going in no particular direction. The closer you are to 0, the weaker you become. 0.5 would be strong or very moderately strong, and negative 0.5 would also be moderately strong. Anything above negative 0.5, technically below negative 0.5 or above positive 0.5 would be strong. Anything kind of close to 0, again, is what we call weak. All right, so here's a couple pictures to kind of get you to understand this. Notice this first picture is very linear, and that would be a very strong positive correlation. This next one does have a little bit of scatter, a couple points that aren't quite fitting the exact linear pattern, so that'd be called moderate positive. This one right here, this guy right here makes it look like it might be positive, but take this point away, and it's just a swarm of bees. I have no idea, no relationship there. Here's moderate negative, here's strong negative, and here's curved. Now, please understand that this data right here is clearly curved, so we would never want to use correlation to measure data like that. Correlation is specifically used for linear data. Here's a couple more examples to show you. When your dots line up in a perfect straight line, that would be a correlation of 1. When they are a little bit looser but still making a nice line, that would be 0.8. 0.3, look at this right here. It's clearly positive. You definitely see them going up, but again, it's pretty weak. There's a lot of scatter there, so that's a correlation of 0.3. 0 is, again, no correlation all over the place. Here's a negative 0.3, here's a negative 0.8, and here's a negative 1. Nice, perfect, and straight. Here's a couple more examples, again, just showing the idea of scatter all over the place. Negative but very weak. Here's a positive but very strong, and then here's another one, negative 0.99, very, very strong. So negative 1 and positive 1 is for a dead perfect straight line. Okay. All right, and here's even a couple more. The only one I really want to talk about here was this one right here. This is going to have a correlation of 0. Now, I see a very strong pattern here, but because it's not linear, it's going to get a correlation of 1. Please make sure that that makes sense to you. Again, I definitely see a pattern, but like the positivity and the negativity of it, way. Notice this one right here looks like literally nothing. I mean, it's a giant swarm of nothingness. But it does have a correlation of 0.08. Well, I mean, 0.08 is extremely, extremely weak. It's very, very close to 0. Whereas this one right here is 0.86. That's pretty strong in a positive direction. Okay? All right, couple final points about R. This might be where you want to pause and take some notes and then listen to me, or listen to me first and then pause. But I'll make a couple final facts about R. First off, correlation, R, they're interchangeable. R means correlation. Correlation makes no distinction between explanatory and response, meaning that correlation doesn't care who you call the explanatory and who you call the response. It doesn't care who you put on the X, who you put on the Y. You could switch the X and switch the Y. Doesn't matter. Your correlation is still the same. So correlation will measure the same relationship whether you call one variable X or one variable Y. Now, you care who's X and who's Y, but R doesn't. R does not change if you change the units of X, Y, or both. If you just convert your units, let's say that you measure in pounds, but then you convert it to kilograms, not going to change R at all. The relationship between those two variables of height and weight are still going to be the same. You could change your inches to feet or your inches to centimeters. And again, the relationship between height and weight is still going to be the same. It's not going to matter if you change the units. R itself has no units. In class, we'll talk about how R is calculated. You're never going to have to worry about how R is actually calculated. It's a very complicated, ugly formula. I'm going to teach you in class how your calculator will find it for you. But just know that there's no units on R at all. They basically cancel out, and R is just a number. Correlation does not imply causation. So even if you have a correlation of 1, a nice perfect straight line, that does not mean that X causes Y. There are always other factors that could change Y, not just X. So please don't ever use the word cause, like X causes Y. Use words like correlated, associated, relationship, tendency, but don't use the word cause. Correlation requires both variables to be quantitative. If one of your variables is categorical, the word correlation is being used out of context, so please don't make that mistake. Correlation only measures the strength of linear relationships. Remember, correlation is only used to measure the strength and the direction of linear relationships. So please make sure that your graph looks somewhat linear. Again, the word somewhat could be kind of vague, but it's got to be somewhat linear. A strong R value, like 0.98 for example, does not guarantee a linear relationship. You could have a graph that has a slight curve to it. Now, R, if calculated, might come back pretty high. Well, because those dots do kind of follow a pretty obvious pattern. But the fact that your eyes see a curve means that you want to avoid using correlation. Even if the correlation is very high, that's just because correlation is a formula that doesn't see what the picture is. You see what the picture is and need to know that that is not linear, so correlation would become meaningless. Lastly, R is not resistant, kind of like mean and standard deviation. It is affected by a few outliers. Just like the mean can get affected by an outlier, so can the standard deviation. R is very much like that. So if you have one point that dramatically does not fit your pattern, the R will naturally become weaker. So the more points that fit the pattern, the stronger R becomes. The more points that don't fit the pattern, the weaker R becomes. Alright, so hopefully that was a pretty quick and easy and painless video over scatter plots and correlation. We will talk a lot more about it in class and do some activities.